Hello, welcome to this video on partial derivatives. It's about the third video in the series, and we're going to look at now higher order partial derivatives. And so we talked about partial derivatives already, and what we looked at was the partial derivative of a function with respect to x and the partial derivative of a function with respect to y. So when it comes to first derivatives, multivariable functions of two variables have two first derivatives. You have to be specific and say with respect to which variable you're taking the derivative to. What about second derivatives? There's multiple ones of those as well. What was the second derivative back in Calc 1? It was the derivative of the derivative. So now, second derivative in Calc 3 is going to be the same, but you have to be specific as to which variable with respect to. So you already take the x partial, and then from that you can take the x partial again. The symbol is a double subscript of x. There is a del notation as well. It's the del x of del f del x, and the del's up top give you del squared, and the del x's on the bottom give you del x squared. I don't really like the del notation, but I just want you to see it and know what it means. It's the derivative with respect to x first, and then the derivative with respect to x of that. But there's another one that comes off of this. You can take the derivative with respect to x first, and then take the derivative with respect to y. It's called a mixed partial. The subscript is xy, and it goes in a regular order from left to right. First is the x partial, and then it is the y partial of that. The symbols for that is the del symbol for that is very strange. It's del y of del f del x. So you get the del squares up top. Down below you don't get the square anymore. It is del y del x, but it's actually backwards. It's performed in the x's first, and then there's y. But if you read it from left to right, it looks like y is first, and then there's x. It turns out that it doesn't matter. I just want you to know the notation and know what it means. And so you could also start with the y partial and take its x partial, or you can do a double y. Take the y partial and take the y partial again. Okay, so through a theorem called Clairaut's theorem, we find out that these mixed partials are equal to each other. Should probably circle that so you can see what I'm saying. Just these two guys. It's called Clairaut's theorem, that the x partial first, then the y partial follow is the same thing as the y partial followed by the x partial. Mixed partials are equal to each other. So it turns out then that there are three different second derivatives of a multivariable function of two variables. The one I like to normally write is xy, but you can write yx as well. Okay, let's go back and just work on some problems on it. Here's a standard, straightforward function, multivariable. A lot of terms that just have an x or a y in it, and that only the first term has an x and a y in it. Let's take this. We're asked to find all the second partials, but you can't get the second partials without first finding the first partials. What's the x partial with these? What's the function's x partial? What is the derivative with respect to x? All the terms that have y only, they give you 0 for their derivative. Even the constant gives you 0 for its derivative. Remember, y is treated like a constant. So that 3x squared y, think of the y like you think the 3. You have that part out front. Focus on the x squared and take its derivative, which is 2x. So you get 6xy. Nothing for the second term. The middle term is a single variable derivative minus 6x. That's your x partial. Now for your y partial, there's three terms that involve a y. The first term has just a y in it. Its derivative is the constant, or the multiplier on it, so it's 3x squared. Second term is a 3y squared, Calc 1 integral derivative, and fourth term is a negative 6y, Calc 1 derivative. All right, what's coming in the future is we're going to be able to set these equal to 0 and find the critical points. And those are possibilities for local max and local min. And so Now we're just going to look at the double x partial. So you're going to start with the x partial and take another x partial. So you're looking at 6xy minus 6x, and you're going to take an x partial. It'll be 6y minus 6. How about the double y partial? You do it with respect to y, then you do it with respect to y again. You focus on the last two terms because they have the y in it, 6y minus 6. This is very strange. Don't expect this to probably ever happen again, but the double x partial is equal to the double y partial. What about the mixed partial? fxy, if we do it in that order, it's already going to be the fact that you're starting with the x partial, which in this case is your 6xy minus 6x, and you're taking the derivative of it with respect to y. The second term has no y's in it. The first term's derivative with respect to y is a 6x. And it should be the same thing. If you started with y and did the x partial, you'll still get the 6x. They're supposed to be equal to each other. All right. Let's take a second function called g that has some same kind of polynomial term, but also has a log term. Let's take the x partial. So the first term's x partial is 2xy cubed. Second term's x partial is quite involved. Natural log of anything has 1 over that same thing as its derivative. Then you multiply by the derivative of that inside, and it's x over y. Like having x over 7, the derivative is 1 over 7. So having x over y, the derivative is 1 over y. And some things happen there. The 1 over x over y becomes y over x, and those two y's cancel each other out. And you get 1 over x. Next up is the y partial. So the first term's derivative is 3y squared times an x squared. Same action happening with the log function, 1 over the inside. But this time when you go to take the derivative of the inside, it's like taking 4 over y's derivative. It's negative 4 over y squared. So it's negative x over y squared. And simplifying, the x's cancel, and one of the y's from the denominator cancel. So you just found your first partials. This question is about your second partials. So let's do the double x. You're looking at the simplified version of the x partial. Now take another x partial with respect, another derivative with respect to x. So 2xy cubed derivative is 6xy. Oh, I'm sorry. 2xy cubed's x derivative is just 2y cubed. And then 1 over x's x derivative is negative 1 over y, x squared. What about the double y partial? That's where you get the 6x squared y. And then minus 1 over y's derivative is 2 over y cubed. Or no. It's like having negative y to the negative 1. So it's negative and a double negative. So plus 1 over y squared. Yeah, y to the negative 2. So that's your double y. What about your mixed partial? Start with x and take a y derivative. That's going to be 6xy squared. It's the same as if you start with y and take the x derivative. All right, great. In an earlier video, we looked at the function arctan of y over x and took its x partial and its y partial. The y partial of that function actually was the function that we looked at on the second big example from a couple videos ago. We've already taken this guy's x partial and y partial. The x partial is y squared minus x squared over that quantity squared, and the y partial is minus 2xy over that quantity squared. And so I was setting you up to be able to look at a mixed partial by the y partial already being this g function, and then us taking the x partial of the g function, we'll have that the fyx is the gx, and the fyy is the gy. So I had set you up for that already. Okay, let's go ahead and end the video here. Where we're headed for the end of this is one quick question, thought-provoking, and then we want to look at what exactly this number is that you get when you take a partial derivative. Thank you for watching. My name is Nakia. Remember, please comment down below, like and subscribe. Reach out to me. I'm here to help. Take care.